Good afternoon, or good noon, good day. Thank you all for coming out today. Southeast Ohio Visitor Center to our second of our Lyseum lunch speaker series. And we're here before you miss to talk about Ohio Canal. Oh, wish you were here for that. Anyway, we have Andy Nash here from Ohio Department of Natural Resources. Vision Geological Survey. He's the mapping group supervisor of the Geological Survey. And he's going to talk to us today about Ohio's glaciers and how they are related to Southeast Ohio before, during, and after. And I'm going to let him tell you anything else he wants to say about himself. And we're all looking forward to hearing about the glaciers. So thank you.
Great.
Thank you all for coming.
All right, thank you for having me, first of all. And I just wanted to kind of jump in a little bit and just give a little bit of an introduction to my talk before it really gets started. So I've titled this The Glacial History of Southeast Ohio, How Multiple Glacial Events Shape the Landscape Around Us. And I thank Tom for that introduction. With the Division of Geological Survey, we're a repository of all geologic information for the state as part of the Department of Natural Resources. So our mission is really archival of all kinds of geologic data. And so I think that translates really well to talking to people who are interested in history, because that's what geology really is the study of Earth's history. And so this picture that I have on the title slide obviously has nothing to do with glacial geology, but I wanted to use it because when people think about the geology of Southeast Ohio, oftentimes the glaciers are an afterthought, or not even really thought of at all. People really think about, especially, these resources that we have, like clay and coal and even oil and gas. So, hopefully this talk will give you guys some good ideas about, that the geology isn't just the bedrock, but also there's a huge imprint from the glaciers that have changed our landscapes from what they were before these glaciations. Part of this photo also is just to say, I've kind of structured this talk a little bit to not only talk about the geology, but what we call geoheritage a little bit. So I'll be talking a little bit, just kind of making some little remarks as I go about kind of the history of geological study and some of the important characters and people who have really helped us understand the environment around us. So a little bit of a more detailed introduction to what I'll be talking about. So the first thing I'm going to really cover is a primer into geologic time, because I know a lot of people don't think about time the same way the geologists do. And with that, I'll kind of give a brief history of the geology of Ohio, and then we'll transition into this ice age as kind of the most recent major geologic event to occur in Ohio. And we'll finish up by talking about kind of what I mentioned, a little bit of landscape evolution, what you actually see today on the landscape. So the first slide, I'm going to throw a very complicated diagram that, if you're not a geologist, it might look a little bit intimidating at first. But this is the geologic time scale. This is how geologists really communicate with each other when they're talking about time. Is we really try to compartmentalize all these different ages and time frames into these different, what we call eras, periods, eons, even, from the largest distinction of time. And so there's a few important eons, and I'll just kind of point out how we use this chart. But the oldest stuff is here in the pink, and the laser pointer might not really work for you today, so I'll just be very descriptive. So that right-hand column that we call the Precambrian, that's a grouping of eons, the Hadean, Archean, and Proterozoic. And this is kind of, geologic time from the start, the beginning of Earth, about 4.6 billion years ago, to almost 550 million years ago. What's significant about this is kind of before life has really taken shape of Earth. And Earth was a very different place at that time, with different processes, a warmer Earth, warmer core, and led to, looking a little bit different, almost more alien than we would know today. And then we get into the Paleozoic eon, which might be more familiar. You see here some of these terms. But this is a time period where at the base of this, the green box on there labeled Cambrian, this is when life really starts to explode on Earth's surface. It's literally called the Cambrian explosion, where we have a great diversifying of species on the planet in the ocean. And building up through that time period, we have lots of evolution occurring where we have different species. You get to the middle of that Paleozoic when you start to get land plants, during the Devonian period, and then animals shortly after those plants colonized the land as well, evolved. And then you get to the Mesozoic, the second column from the left. And this is, everybody kind of knows these time periods, as the dinosaurs are roaming there. They're really, taking hold of kind of all of the geologic interests for most people. Those terms like Jurassic and Cretaceous. We know a lot about the dinosaurs, and they go extinct right at the end of the Cretaceous. And then we get into this Cenozoic, this left-hand column in yellow. This is the most kind of modern time. This is where Earth is really kind of looking like we know it today. And then we have this little sliver of time here at the top called the Quaternary, which is what we're living through today. And this is really the Ice Age. And so you can imagine, when we look at all this time and everything I've kind of talked about, as far as like a metaphor, if you were to put your arms out and kind of measure your wingspan and think about geological time, the start of the Earth on the right hand here, what we're living through right now is like a sliver, a nail file, cuts off your finger. It's just that little clipping, essentially, that really small piece of time. So geologic time is really huge and hard to kind of think about and imagine. But I'm going to be kind of throwing out terms, millions of years ago, or hundreds of millions of years ago, and that's kind of hard to fathom sometimes. So as geologists, we're kind of deep thinkers and thinking about time in these really long time scales. So I wanted to kind of give a brief overview of Ohio's geologic history, just to kind of bring everybody up to speed of what was happening for billions of years. And so this map that I'm showing here shows the pre-Cambrian geology of this continent we call Laurentia. And this is North America before North America even really exists. And all these rocks are still kind of underneath us today, in Ohio at least. In some places in North America, they're exposed at the surface. But in Ohio, these are going to be buried 3,000 to 10,000 feet or more beneath our younger rocks. And so this North American craton, as we kind of can call it, and these colored areas here are all composed of igneous and metamorphic rocks. So these are the rocks that form from like magma, lava, and then they can, the igneous rocks. Metamorphic rocks are formed when you undertake heat and pressure to those other types of rocks, igneous and sedimentary, to realign minerals, stretch out minerals, or change the texture of the rock. So, as I said, these are exposed to some parts of Canada, but today they're going to be deep within what we kind of call the basement. These are kind of the rocks that, if you're interested in kind of the geology, and especially drilling deep, you typically don't go any deeper than this, because these igneous rocks are just kind of like the deepest that you can get. And so you can see the Great Lakes actually on this map to maybe help orient yourself with the Fond Lake Erie. You'll see that Ohio is kind of in this granite and rhyolite province, and also adjacent to the Grenville province. And so these rocks formed about 1.5 to 1 billion years ago. And the Grenville province is really a mountain building event that occurred about 1 billion years ago. And what that does is kind of set the stage for the Paleozoic, as we'll talk about next. Because you have this mountain building event to the east, that helps create kind of a basin out to the west, where we can start depositing these Paleozoic rocks. And so the Paleozoic, as I kind of mentioned, this is the time where life really takes hold on our surface, and we get this explosion in diversity of life. And the Paleozoic history of Ohio is pretty interesting, because we have this time period of about 230 million years recorded within our rocks. moving from the Ordovician to the Permian period, from younger to older there. And you can see these color codes to the map on the rocks on the map there. And one thing that's interesting of note is that if you were to put in Pennsylvania, West Virginia, and Kentucky kind of into this map and look a little bit more regionally, you'll see that these rocks make a big bullseye pattern. And these rocks that we find in Athens, of Pennsylvania age, wrap around these other states to kind of form, like I said, kind of a bullseye. And that's because these rocks are all being deposited in this basin, what we call the Appalachian Basin. You know, as mountain building events are occurring to our east, building the Appalachian Mountains, that's pushing up the mountains to our east, but depressing the land over Ohio, creating what we call this basin, or sometimes we'll hear it called the Foreland Basin. And so all that material is falling into that basin and being deposited as sediments, and over time, it lithifies or turns into rock, as we see it today. So, you know, this Paleozoic time period, one thing about Ohio is interesting is if you're driving from west to east, you're going to be driving over rocks that get younger as you move. And so in the Cincinnati region, we have these Ordovician bedrocks, well renowned for fossils in the limestone, things like brachiopods and trilobites and crinoids, all these really interesting species that lived in the oceans at that time. But then as we move to southeast Ohio, and we go through almost 200 million years of geologic time, we get to a more terrestrial landscape. So these rocks are being deposited after the mountains have really been fully formed, and then this area has been uplifted out of the sea, and we are kind of in a coastal swampy environment during the Pennsylvanian, and we kind of alternate back and forth a little bit between being underwater and being above water, and that's where we kind of get these coal slumps. So Ohio during this time would have been near the equator. Plate tectonics hadn't moved it north of the equator until you get into that Pennsylvania time period, and even then it's just right about the equator. So we've got a really nice tropical, you know, kind of environment. It'd be like Jamaica today, but at that time, you've got these giant kind of coal slumps forming, and we see that when we look at the geology of the area. And so, you know, one of the best places to really just drive and see the geology change very quickly is actually the Nelsonville bypass. I'm probably preaching to the choir a little bit here, but you can see these amazing rock outcrops that were created when the bypass was put in. And as you drive, if you make kind of careful observations, you'll notice that those rocks change very rapidly. And so that's kind of the story of this Pennsylvania period, is that we go from coal to shale to sandstone to siltstone. You see all these different types of rocks in these rock walls, and you can go from a mile down the road and you see, oh, there's a change, the rocks look different. And that's you know, one reason why when we map these areas, we make big general assumptions, and we group things together a lot when we talk about these rocks in these areas, saying they're from, you know, an Allegheny group or a Pottsville group. You know, you might see those terms on a geology map. And then other places in Ohio, we've got things very neatly split out where we say this is this rock and this is this one. But in this area, that's a lot harder to do. So as I mentioned kind of at the beginning, you know, when people think about Southeast Ohio and the geology of Southeast Ohio, they really think about the Paleozoic bedrock resources first. So this is a photo from 1957 of an abandoned strip mine. This is from York Township in Athens County, near Door Run. This actually comes from Bulletin 57. You can find the exact figure and page here. And that gives you information about the geology of Athens County in that bulletin. And what you see in this picture is kind of more of what I was talking about here on a very fine scale. So this is annotated by the original author, Robert Begney, and you can see that the coals that were being mined are labeled here, and in between these coals there are underclays, or different kind of clay layers. And so what you see often with this kind of resource that people are looking at is, well, they want to mine the coal, but those coal seams are usually only a few feet thick. You know, you might get lucky and get a 10-foot thick coal seam in some areas, but for the most part, they're 3 to 5 feet thick on average. But there are multiple of them stacked up, so you can mine a hillside, and then you've got all this clay to deal with. Well, people in Southeast Ohio in the late 1800s and early 1900s knew exactly what to do with that. Turn it into bricks. So I'm sure you see Nelson pavers, Athens block, all over. And that's probably a story that's been told multiple times. But what really hasn't been told is what happened after the Paleozoic ended. That ended, if you remember, about 250 million years ago. And then we had glaciers start about 2 million years ago. So we're missing 250 million years of geologic time where dinosaurs roamed the earth, but we have no rocks to record that record in Ohio. Our rock record really ends 250 million years ago. And so we make maps at the Geological Survey where we're not only focused on the bedrock geology or the lithology of rocks, the types of rocks, but we're really interested in their elevation as well. And that's these bedrock topography maps here. And these elevation maps are useful for us because we can use them to kind of determine what was the pre-glacial environment like in Ohio before these glaciers came through and changed the landscape. And so this map here represents that pre-glacial topography with these colors representing different elevations. You'll notice there's a red line that kind of separates Southeast Ohio from Northeast, Northwest, and Western Ohio. And that's that line of what we'll call like the glacial limit or the glacial maximum. So this is the maximum extent that any glacier really reached. And when you go south or east of that line, your land surface elevation is essentially equal to the bedrock surface elevation. So if you live around Athens County and you're on the top of a hill and you dig down a little bit, you're going to get to rock very quickly. If you're in a valley, it might take you a little bit longer, but if you're places in Western Ohio, there's entire counties where you can dig down 50 feet and not encounter any bedrock because those glacial materials have been spread over the entire landscape. And so this map was completed in 2003 by Scott Brockman and others. And here's actually a photo of Scott. Scott retired pretty recently within the last decade. But he spent a lot of his career in the 80s and 90s working on this bedrock topography mapping. And you can see him drafting a map by hand here. What he's doing is looking at bedrock wells and the depths of bedrock recorded in those wells, and then drawing contour lines around them. So this was a labor-intensive process that took geologists, cartographers, graphic designers, editors, all kinds of different people to manage all of these maps, all of these papers. Librarians and archivists manage them today, and did as well then. And we still have all of these original working maps archived at the Geological Survey. So they're a really nice, important resource for us, and they were turned into that digital map product that I showed earlier. Today, I just have to put on my salesman hat just a little bit because I like to do that sometimes. But we have modern mapping efforts that we're doing that we really improved on. While those older classic maps are great, we know that the resolution can be improved with new technology. And this Tremino device here is one of those pieces of technology that we currently employ. This is an instrument that measures earthquakes. Within this box, there are 3 little weights on springs. And as sound waves travel through the earth, you can see in the little cartoon on the right, cars and people, helicopters, a jackhammer, they create sound waves that travel through the earth. And as they move through and bounce off the bedrock, they can be received by this device, and those sound waves, this device is so finely calibrated that you can record those sound waves by moving that weight up and down in the spring. And we can use that to calculate how deep it gets to bedrock. So what we can do with this device is set it on the ground for 15 minutes, press play, walk away from it, and then when we come back and it's done recording, we can take it to the next site And when we're done from it for a day, we can collect, 15, 20, 25 points in a day pretty easily sometimes. We can take those back to the office and process that data and get the depth of bedrock and even some information about what that material actually is in the subsurface much easier. So we've actually collected thousands of points since 2017. We're about to cross the 10,000 point mark, mostly in Western Ohio where the bedrock topography is deeper. But we have done a little bit of work in Coshocton and Perry County as well. So we've kind of represented Southeast Ohio a little bit there. But what we're really doing and working on is improving this kind of really classic map. And this is a map that was completed in the 40s to show the Taze River Valley. And this is really Ohio's first bedrock topography map. So when we're thinking about that land surface that existed between the deposition of rocks and the glaciers, this is kind of our last snapshot of what that landscape would have looked like. We don't know as much about what was happening 200 million years ago, but these glacial deposits have buried and preserved the bedrock surface to show us what it kind of looked like maybe 10 million years ago. And so we know that there was this large valley called the Taze River Valley that flowed from its headwaters in North Carolina through West Virginia and Kentucky and into Ohio. And you can see the path, this solid black line here is the Taze Valley, comes through Southeast Ohio, kind of up into Ohio through Lawrence County, Scioto County there. And this predates the Ohio River. If you'll notice that there are different tributaries, and especially an easy one to see near Manchester and Adams County. And that is a drainage divide where water falls on either side of that line. It'll move either east or west depending on which side it's on. And so the Ohio River did not really exist at this time before glaciations. Like I said, this age of the valley is kind of unknown. The exact age isn't really known. But we do know that, just conceptually, these Appalachian Mountains formed about 250 million years ago. They kind of reached their kind of final form as we know them today, and then they began eroding into what we literally know today. And as that erosion occurs, these rivers and streams are going to become organized and form this Taze River. So there was probably early iterations of this river kind of forming as soon as those mountains finished. And everything kind of flowed up this direction and eventually out west to the ancestral Mississippi River. So I wanted to kind of insert a little bit of geoheritage here. So Wilbur Stout is a famous geologist, really one of the most prolific geologists that we know today, who worked in Ohio. He was our 6th state geologist. So he served during the Great Depression and World War II as a state geologist. And during that time, resources were obviously extremely limited by the Depression and then into the war era. And at that time, he was able to publish nearly 50 papers over many topics. He had a lot of focus on Southeast Ohio, doing specific county studies in Muskingum, Columbia, and Benton County. And he published Bulletin 44, the Geology of Water in Ohio, which is really a classic hydrogeology publication and is still seen as a very useful publication. It's one that we at the survey have hopes and dreams of improving on with modern technology and coming out with kind of a new version of that. But it's amazing what he was able to do and work on doing these large statewide projects about all kinds of resources, coal resource assessments, with really just him and a few assistants. At many times during this time period, there were only 3 or 4 employees of the Ohio Geological Survey. And it was after his kind of reign in the late 40s and early 50s that DNR was established. We're actually coming up with the 75th anniversary of DNR next year. And the Ohio Geological Survey kind of got into a little bit more funding that way. So here's a photo from Overstout, actually. This is from our photo archive. This is an old Tate Stage Valley near Albany and Athens County. What you're looking at is the wide width of this valley really obscures kind of what we really think of for Southeast Ohio. You know, if I were to show this photo to somebody, they probably wouldn't guess this came from Southeast Ohio. What we're looking at is kind of directly upstream, looking kind of south to north, and you can see this slow rise and slope as you move into the horizon. And that stream valley would have been coming right at us, water would have been flowing right at us. It was abandoned, you know, probably more, what we can say is really more than 780,000 years ago, but likely more than 1 million years ago. And over time, we've had modern erosion for the last 1 million years that has kind of turned this, what used to be a flat kind of floodplain, into this kind of rolling hills and valleys, almost looking like kind of small dots on the landscape. So I've kind of talked about it a little bit, but I really want to formally define the Quaternary period. So the Quaternary period is our last 2.6 million years, just about. And it's broken up into two epochs, the Pleistocene and the Holocene. And our most recent kind of time period, the Holocene, actually that word has a French origin meaning entirely recent. So this is kind of a global warm period. It's really marked by these millennial scales, so like 1,000-year changes, fluctuations in climate, and then of course societal development. You know, I think a lot of what we look at around us in the History Center, you know, is really going to fall into this. You know, we think about like a kind of more modern natural history or human history. But before that, we have the Pleistocene, and this is kind of the formal term for what we might say informally is the Ice Age. And so we have these global climate oscillations based on Earth's orbit around the sun. It kind of vary in 3 different parts. You know, basically how elliptical is the orbit, what kind of tilt did Earth have, how much did it wobble on that tilt. When you combine all those things together, you kind of vary on an almost 100,000 year time period, back and forth between a glacial time period and an interglacial time period or warm period. And so in Ohio, we really recognize 3 Pleistocene glaciations. It's really more than that, but when we think about this kind of as a formal kind of way in the geology, we think about these 3 glaciations. The last glaciation was the Wisconsin glaciation. This occurred for about 35,000 years ago to about 10 years ago. Before that, what we call the penultimate glaciation is the Illinois glaciation. This occurred from about 200,000 years ago to about 130,000 years ago. And then lastly, we have the pre-Illinois glaciations. And so you might see, if you read older texts, references to what we call a Kansan or Nebraskan glaciation. There's even an Iowan glaciation if you go further out west. These glaciations were older than 780,000 years ago. The one thing you'll notice as we kind of step back in time, our ages get less and less precise. And that really has to do with the methods that we have to get an absolute age dating. So most people will probably be familiar with radiocarbon dating, and that's the process of taking carbon that's within an object or a plant fossil, bones, shells, things like that that contain natural carbon, and that gives us an absolute age by running that through some fancy chemistry that I can talk about more if you want, but suffice to say it's pretty complicated. For the Illinois glaciation, we only really have one method. That radiocarbon dating is really only good to a maximum of 50,000 years ago. The Illinois glaciation, we have another very complicated method that we can use to excite the electrons that are stored in the quartz crystal. And those electrons, through radioactive decay, get trapped in a quartz crystal. And the more electrons that are trapped in there, the older it is. And that's kind of a real basic summation of what we call optically stimulated luminescence, or OSLD. And it has a wider range of error compared to that radiocarbon dating. And then for pre-Illinois glaciation, the only method we really have to tell how old some of these glaciers, glacial sediments are, is whether or not they are magnetically reversed. And so this is kind of an interesting kind of theory, but we know that we are magnetic north, points north today. That always isn't the case. It flops between the poles over different time periods. The last time that changed in what we call a reverse polarity, where magnetic north was actually south, was 781,000 years ago. And so during that reversal, we can look at sediments, a lot of them in southeast Ohio, and you look at the magnetic minerals within those sediments, they are oriented pointing towards that kind of south pole orientation. And so we know that they are older than 781,000 years ago, but we can't tell you exactly how old they are. And that's one reason why we stopped saying Kansas and Nebraska and just call everything pre-Illinois, because it's too hard to kind of tell them apart without that absolute control. So a little bit more about the Pleistocene epoch, especially within the Wisconsin glaciation. This is kind of artistic representations of what that would have looked like during the Wisconsin glaciation, kind of at its maximum extent. And so we would have been looking at an environment that's very similar to Greenland or Antarctica. And you can kind of see from these maps that Ohio right here is kind of at the southern edge of that what we call the Laurentide ice sheet. This North American ice sheet, continental ice sheet that went all the way from the Canadian Rockies to the Atlantic Ocean. And here in Ohio, we have what are called lobes and sublobes. And so the ice, if you just look at this artistic rendition in the lower left, it looks like a big solid mass of ice. But what we really know is behaving is this ice is moving very slowly, but it is kind of behaving as it's flowing downhill, somewhat like a liquid. And so that wants to find the easiest way that it can flow, its path of least resistance. And as it does that, it fits into what we call these lobes and sublobes. And so Ohio was covered by the Huron-Erie lobe, which named for the Great Lakes that it covered. But then we have these sublobes where this encountered resistance to flow from different topographic obstacles. The main one that we'll kind of talk about, you see the difference between the Miami and the Cider lobe, named for the rivers that they covered, modern rivers. There was a split at Bell Fountain, the highest point in Ohio right there. And when the ice reached that Bell Fountain outlier, they had to go around before it could kind of go over. And that split us into these two sublobes, the Scioto and the Miami sublobes. And the Scioto sublobe had the most influence on southeast Ohio. So whenever I kind of talk about throughout the rest of the talk, that glacial influence, I'm really referring to that Scioto sublobe for the most part. And so this is a block diagram just to kind of introduce glacial deposition and how glaciers kind of begin to kind of change those environments by depositing sediments. So here we're showing a glacier that is already retreating. It had reached this in moraine, this ridge of glacial till here, and deposited that material. Glacial till is just a mix of kind of everything. It's clay, silt, sand, gravel, boulders. I mean, blocks of rock the size of VW Beetles are moved by these glaciers, bigger sometimes. And so they all get mixed together and deposited either directly by the ice or as the ice melts out in a couple of different ways. But the key point of that glacial till is that it's a really heterogeneous sediment. Essentially, it has grain sizes kind of all, or particles and rocks of all grain sizes. And it can form in a couple different landforms. When we see it in these ridges, we know that the glacier was paused for a short period of time, forming those ridges. And one key thing about glaciers to know is that they're like a giant conveyor belt. They're always moving, even if they're kind of stationary. If we're observing a glacier as stationary and not moving, that ice is still being pulled by gravity to the front and then melting away, and new ice behind it is infilling that area and bringing new sediment up to the front. You can kind of see that here as well, as we're kind of showing these sheets of till underneath the ice, and then the piles of sediment kind of at the icy margin. But, you know, we don't just have sediments that are directly deposited by the ice. We have this melting of the glacier that occurs yearly and seasonally, and especially at the end of glaciations as glaciers are retreating. And this forms in these valleys that we call outwash valleys. An outwash essentially just means as that glacier melts, water carries it away from the glacier in a river, and it washes out all of that sediment. And what we're left with then is a sorting of the sediment. So it's different from that till, which can't just include kind of everything. Outwash is going to be primarily sand and gravel, because the water has a little bit less force to kind of move material than the glacier does. So it's kind of selecting and sorting some of that stuff out, and that sand and gravel is actually dropping out of suspension in the water and getting deposited. And that moves away from that glacier. You can see the end moraine, whereas the end of that glaciation, the outwash is moving past it. So we see that throughout southeast Ohio and other parts of Ohio where even though the glacier didn't reach this area, glacial material is being transported through in unglaciated terrain. And so the early Pleistocene, I kind of just want to go chronologically now through kind of these different glaciations and time periods. And so we look at maps like this just to look at statewide kind of the glacial history. And you can see this green color is the Wisconsin episode. That covers most of Ohio. It's the last glaciation, so it's kind of on top of everything else. Then we have the Illinois episode in this kind of lighter purple pinkish color. And you can see it just kind of pokes out along the margins. It reached a little bit further than Wisconsin in most places. And so you can kind of see that margin extended a little past Wisconsin. But there's probably Illinois sediments either beneath the Wisconsin glacial sediments, or they're mixed up within the glacial sediments and redeposited as all kind of this Wisconsin age. You'll notice the pre-Illinois deposits in Ohio on this map are only shown west of Cincinnati. And so this is the only place that we have these pre-Illinois glaciations, remember that Kansas, Nebraska terminology, in Ohio. Except that's not really true. When you look at a map like this, often you'll see, for the glacial geology of Ohio, southeast Ohio is just called unglaciated. There's nothing going on, it's just a lake. And so it's often really overlooked when it comes to this glacial geology. And whoever made this map did a really bad job and just was a little bit lazy. So, but sometimes when you're, obviously focusing on a specific topic, especially a very broad topic like just Wisconsin glaciation, it gets really complicated in southeast Ohio. And these units are very small, and we can't really show them on a map like this. And so they kind of just get left out and are that afterthought. But we know that there were lots of deposits in southeast Ohio, and there are lots of events. The first event I want to talk about happened during that pre-Illinois glaciation. And you can see on this map, this is a relatively recent map by Jim Urjevich, who is Southeast Ohio native, and actually works down in Piketon for the Department of Energy. But he undertook this project to update some older mapping of Lake Type. And so you can see the green line is that limit of glaciation. On the red line is our Taze River, which are kind of labeled with those call-outs. And all this blue here is what Lake Type would have looked like at its maximum extent. It probably didn't look like this all the time, but it was probably patchworks of multiple lakes occurring at different time periods. But from our kind of perspective, almost 1 million years ago, it's pretty hard to tell a difference between a lake that was, just a few thousand years older than another. So what would have happened is that you had that ice come down, that first ice that came into Canada during the pre-Illinois glaciations, dammed up this Taze River that was flowing to the north. And so all that water coming south to north of the Taze can't go anywhere because it's hitting that ice dam right there. And then you have water melting off the glacier into the same area. Between those two factors, you start to flood the entire area. And you can see on this map, there's some yellow colors kind of throughout there. Those are the mapped areas of the lake. sediment. And we can see that on our maps that we have created with the Ohio Geological Survey. And then you also have these areas of ground which would have been islands kind of sticking out. These are the high areas that the lake waters weren't able to actually rise over. And so this mapping, as I mentioned, is kind of an update to previous mapping. And so this is an older historical map from W.G. Tite. It came from one of his really best manuscripts published by the United States Geological Survey, where he undertook a mapping project around the turn of the century, published in 1903, where he tried to map out, based on the deposits of all those silts and clays that would have formed in this lake. And he was really the first to kind of recognize those as being of a lake, how big that lake would have been. And you can see on his map, these narrow channels are kind of the lake. And so, you know, he was really based on some of this mapping. He was doing a lot of this work even without topographic maps in some places. So he was severely limited. But for what he had, he did a really remarkable job of at least kind of getting the extent of this lake, which now bears his name. So William Tite is kind of an interesting character, so I wanted to talk a little bit about him. He was a professor at Denison University, born in Granville, where Denison is. He was a geomorphologist, so he and I have very similar interests, where a geomorphologist studies these landscapes and potentially how they change over time. And he was the first person to describe this Glacial lake. And he was a professor at Denison for 14 years, until he finished his PhD at the University of Chicago in 1901. At that point, he abruptly uprooted his life and left his family and moved to New Mexico to serve as the third president of the University of New Mexico. You can see over that 8-year time period, he actually had a huge impact into the university. He established the Pueblo building style that the University of New Mexico is famous for. He was the first to introduce full regalia at commencement ceremonies, and he introduced Greek life to the university. So these are lasting effects that you think would leave a great legacy. But unfortunately, he was dismissed by the Board of Regents in 1909, and it's not really well known why, but you know, people whisper political reasons. And then he shortly passed after this dismissal, just a few months at the age of 45. So kind of a sad end to life, especially because there was a campus fire in 1910 that destroyed most of his papers and correspondence. And therefore, it's hard to find a lot of information about William Tite. And this has actually led sometimes to conspiracy theories about Lake Tite and its existence and kind of cover up, things like that. But for the most part, it's a widely accepted theory for this Glacial lake. And so this is what Tite was really looking at, was this Menford silt, is what it's called. Is anybody familiar with the town of Menford, or that general area? Yeah, some people are. And so it's over a little bit further west from here, near Scioto County, in between the Scioto River and what was the Taze River. And so this really finely laminated silt, you can see the scale here, you know, just a few millimeters on some of those fine laminations. Is really that strong evidence that this was deposited in a nice, calm, quiet lake environment. You can see as you kind of dig into it, really how homogeneous this Menford silt and clay really is. And we see with the Taze River a major drainage reorganization after this lake type was to had occurred. And that happens when you get these coals, or little kind of low spots on a ridge, essentially, that when you have those glacial lakes rise up to that level, they overtop that and create a spillway and can cut through and erode that rock and create a new drainage. So essentially, I'm trying to go a little fast because I'm a little bit behind on time, but this glacial lake can form, as we see here with the glacier, and as it reaches that drainage divide, it can spill over, and when the glacier is gone, and we're left with just the glacial deposits where it was, we can see some remnants of that glacial lake in the sediment terraces. It might be like the Menford clay, but now we've got this pre-glacial stream that used to go north, is now going out to the east and then eventually south. And so we see this all over Southeast Ohio. Really an important, famous one, of course, the Ohio River breached two different drainage divides, as I showed earlier from the Tays, and now flows in the southwest to western direction across what we know today. And these valleys were tributary valleys before. As I mentioned, down near Manchester and Adams County, you had water going in opposite directions. Now that was overtopped there and cut down to form this new channel. This also happened on the Muskingum River, right there in Southeast Ohio. So this really happened a lot. This is looking at the post-Wisconsin stage when ice is right there at its maximum extent. You can see what those rivers kind of looked like at that time on this map. So these stream reversals work in two ways, whether it's an ice dam blocking it up, or whether it's outwash that builds up. And in some valleys, this is an example from Tuscarawas County, you get these large valleys that are carrying outwash away from the glaciers, but then you have these small tributaries that are still flowing into them, but they don't have enough sediment to kind of keep up with that rise and outwash that's building up, what we call aggradation, in the main valley. And you can create a dam with that sand and gravel material with lake behind it, and then overtop that same kind of drainage divide to cut a new spillway and reorganize the way that water flows in those surface streams. And so we call these slackwater lakes. One thing, if you look at, this is Burr Oak State Park and the reservoir there, it looks very similar today as what a slackwater lake would look like. Where we built an earthen dam right there, you can imagine if there was outwash that came to this valley and built up, you would get a lake that looks very similar. So this is kind of an analog to what those slackwater lakes would have looked like. If you're curious, they would have looked a lot like our man-made reservoirs do today, where they just didn't fill those low spots in the valleys and follow that drainage. So to kind of close out, so I'm going a little bit faster, but I want to leave some time for questions. We're just going to talk about some of the sediments and landforms that are left behind during that glacial period that we see today. And so I've talked about lacustrine, silt, and clay a little bit, but I wanted to mention too that there's a special kind of form that we call barbs that you might have heard of. Sometimes if you get a seasonal kind of change, you can actually deposit a yearly packet of sediment that's identifiable, where you go from a clay in one season to a sand in another, and you stack those on top of each other. You can use them like tree rings to figure out how old that lake was. And so we can do that a little bit in Ohio, but it's mainly done in the northeast parts of the country, Maine through Massachusetts, where they've been able to kind of use a chronology to know exactly when glaciers were where based on these lake bars. Then we also have glacial outwash, which we've covered on a lot. There's another picture of Lower Stout in southeast Ohio. Back in the 1930s, they did fieldwork in suits, which I don't know if I would be really willing to do today, but it's a different time, right? It's still a very cool picture. Yeah, exactly. But they, these landforms, or these sediments, form in landforms that we see today called terraces. And I mentioned these a little bit earlier, but you can imagine you've got this flat surface here, which is like a modern floodplain, and then these sheep are on this little rise here. You can look at the rise in the background with a nice flat surface. These are terraces, and when we look here, this is a map derived from a digital elevation map, that we call it. So this is kind of a better version of a topographic map because it allows you to visualize the landforms a lot more clearly. And so those white colors are kind of the high tops of the ridges, and the kind of light green to light blue colors are the low areas. Sorry, it's a little washed out, the colors a little bit. But those are the low areas of the modern streams. And you can see I've got 33 kind of labeled here, and this is the Hocking River. And these labels, A, B, and C, are three different terraces that you can see in kind of one snapshot. And so A is the lowest elevation. That's a Wisconsin age or even post-glacial terrace that has been abandoned recently, and the river has kind of down cut through it. B is an Illinois age terrace, so this is from that penultimate glaciation. And then C is a terrace that was formed during lake tide time. And so you actually had lake type kind of sitting right there, and you can find Medford silt sediments in those terraces. And you'll notice that these are much different elevations, but we can kind of get an idea of how old they are based on those elevations. Because rivers have been eroding and down-cutting through time, and then we've had changing sea levels as well on top of that, we generally know kind of that trajectory of those terraces, how old they are in their elevation. So when we kind of zoom in, you can see some interesting things here. So does anyone have a guess what these two little dots are on this terrace? Mounds, yeah, exactly. This is a really great tool, actually, for seeing mounds and seeing Native American settlements, this digital elevation model. One thing that we've been working on is, at the Geological Survey, is partnering with the Ohio History Connection. They keep a database of mounds, and whenever we see them, when we're doing our mapping, we mark their location and send them those locations. Oftentimes, we'll add mounds to their database that they didn't know about, just because we see them from our office doing our mapping. So this is actually Hartman Mounds at the Plains. That's that terrace right there, that Illinois terrace is the Plains. So if you're familiar with that area, or if you live in that area even, you live right on top of glacial outwash that is probably 160 to 130,000 years old. So it's a pretty cool area there. It's pretty cool that you can kind of see those mounds from space, as it were, from the sky with the digital elevation model. We also have loess in this part of the world. Loess is a wind-blown silt. So as that outwash is moving down its valleys, it gets stranded on floodplains and picked up by the wind, and then blown onto the tops of ridges. So you can see on this map here, here's Athens for kind of reference on the Hocking River. And then you see the same elevation where you've got the highest hills are kind of red here, but there are these loess deposits that are pulled out from soil maps that you can see over most of those ridge tops. They follow the ridge tops pretty well. In some areas, they map loess in the floodplains. And that's just a kind of a quirk of some of the soil mapping. But essentially, most of the true loess that we see that's glacially derived is actually coming from that Hocking River outwash. And then lastly, excuse me, lots of talking. The post-glacial and non-glacial deposits are kind of the eons, as I like to call them, the alluvium, the colluvium, and the residual. And this is kind of a process that all kinds of works together. So you have residuum, it's the residual material that's forming at the top of those hills, the more stable hilltops and ridges. Then you have colluvium, which is your hill slope deposit, seen in this picture to the left, where you think of like landslides kind of moving by gravity, pulled down the valley. And then finally, the alluvium, through that process, it uses water, rivers, to carry that material that's pulled down by gravity away through a valley. And so that's a major kind of thing that's happening in Southeast Ohio, even during the glaciations, before the glaciations. It doesn't really stop with the glaciations, and sometimes it might actually be sped up because we have more water moving through the system. It's colder, you have things like freeze thaw that's destabilizing slopes. And so we see this kind of day, still happening. These are one of these geologic processes that kind of always happen slowly in the background. So I have a couple of conclusions. First conclusion is although Southeast Ohio was never glaciated, the Ice Age had a major effect on the landscape we see today. We've kind of talked about that. The main way that we move sediments through Southeast Ohio is through that meltwater. And here, in this particular part of the world, that's through the Hocking River. So the Hocking River is really carrying a lot of those sediments down eventually to the Ohio River, at least past the last glaciation, or during the last glaciation. The Taze River, which had a northwest flow, was reversed after the lake type overtopped poles and cut a new valley at lower elevations. This eventually became the Ohio River with a southwest flow. So you can see in this photo here, this is the black line, the modern side of the river coming to the south, and the gold line is the Taze River, the path that it followed moving to the north in this part of the world. You can see they occupied the same valley at some point. There are terraces, again, on that northwest side of the valley there, where the Ohio, or the Scioto River, excuse me, doesn't cut through anymore, and these are left high, abandoned, flat terraces or remnants of that valley. And then you can see through here, 32, just west of that Jackson label, kind of cuts through that old lake-type valley and goes through and piped in there into the Scioto River. This is it's what we call an abandoned channel. And so there's only a really tiny stream in that channel now today. So it's really kind of an impressive landform when you drive over. It's kind of confusing why you've got this big valley, this tiny ditch-like stream. But now you know why, because of that reversal. And finally, the sediments that are deposited by water, lakes, and rivers, these are the most significant quaternary glacial deposits in southeast Ohio. We, of course, have really significant colluvium and alluvium, but as far as these glacial deposits, we're really focused on these glacial lake deposits and glacial outlet deposits. With that, I've got a few selected references if you're interested in learning more about what I've talked about today. These can all be found either through our website, our publications catalog, or through the Ohio State Knowledge Bank, where PDF and scanned copies are freely available online. With that, I say thank you, and I will answer any questions that you have. It was a large topic that I only had an hour to go through, so I left a lot of stuff out, so there definitely could be some questions, but thank you. Lastly, before I get too sidetracked, I do want to say I brought a couple things with me today. We've got leaflets that talk about the Ice Age in Ohio. We can pass these out if you're interested in these. They're especially great for kids. I also have 3 king-size maps that have been archaeology, the quaternary geology, and the physiographic regions of Ohio. These are really great maps that we have full wall versions as well if you're interested in for decoration. I also have, these are topographic maps of the Plains quadrangle. Unfortunately, it's a funny story. We have all of these topographic maps that nobody really wants anymore. Nobody wants to work with paper maps. And so we went through a process of starting to recycle them. And unfortunately, the Athens quadrangle being alphabetically near the top got recycled first. Then we said, stop, no, we actually don't want to recycle them. We'll give them away for free. So I didn't have any Athens quadrangles to bring, unfortunately, but I do have some. So if you're interested, after I'm done with questions, please come take some. I'd love to not take any. So, thank you. So please question.